Welcome to this installment of the Deploy IPv6 series. My name is Tim Rooney, Director of Product Management at Diamond IP, and the goal of this video series is to break into bite-sized chunks IPv6 technologies and techniques. This video is part 3 of a set of videos talking about IP address block management. In this video, we're going to talk about IPv6 address planning in particular. This video builds on what we covered in part 1, which talked about the motivation for IP address block management in the first place, why you should be concerned with it, and some of the benefits of doing so. In part 2, we talked about some of the tactics and mechanics of address block management, and we also demonstrated our multi-layer IPv6 subnet calculator, which you may also want to access after viewing this video to play around with various alternative plans that you might have in place for your IPv6 deployment. What we're going to discuss in this video is we're going to start out talking about some of the goals of an IP address plan in general, and IPv6 in particular. We'll talk about some IPv6 address plan guidelines that we'd like to recommend, and we'll also demonstrate those guidelines through a couple of example IPv6 address plans, and then wrap it up with some resources, including a pointer to that aforementioned calculator. The goals of an IP address plan, first and foremost, is to allocate IP addresses to those who need IP addresses to access your network. So basically allocating IP address capacity for infrastructure, routers, switches, etc., and end user devices, those end users, associates, partners, subscribers to whom you want to grant access to your IP network. Second goal is to enable these end nodes to communicate with each other or not. So you may have the ability to refine which end users can access which resources, for example. Perhaps you want only a certain number of administrators to access your cloud infrastructure, maybe a certain access to your Internet of Things subnetwork if you've got that cordoned off separately, or even access various components within your network, such as the finance department's servers and so forth. A third goal is to enable Internet or partner communications, or not. So typically we have the view of our common enterprise deployment of a network address translation or NAT firewall on the perimeter of a network, interfacing the enterprise network to the Internet or to a service provider. And typically that provides the filtering functionality and also address translation in some cases to communicate securely and to detect potential attacks and to limit traffic flow in either direction. And that is largely based on IP addresses and also ports that are used by the transport layer. But basically the IP address plan, certainly because of that, will play a key role in terms of enabling that communications and controlling that communications. Likewise, enabling communications via supported media or applications. So in our first video, we talked about source address dependent routing, where you may configure your routers to perform certain prioritization of packets with certain characteristics, such as those with a source IP address, really from the voice over IP address space, for example. So if you separated address space for certain applications that require special treatment, your routers can be configured to apply such treatment based on those policies and based on that source IP address. Also, another goal is to facilitate network management. So it's great to have a plan to start out with, but how is it going to really help you manage your network on an ongoing basis? And as we'll see, the IP address plan can vastly help you simplify network management as well as security management. As we alluded to just a moment ago, the network address translation firewall typically bases a lot of its decision making on IP addresses, inbound and out, source and destination, among other things. But the address plan certainly plays a role in that, as well as access control lists and other IP address-based policies. So the implications of IP addressing on your overall operations of your network, if you talk about, again, the end devices, every device that is assigned an address must be assigned an address, of course, that is relevant to the point of which they're attaching to the network. So the particular subnet, so that it can have its traffic routed bidirectionally as appropriate. The media type, again, based on the source address dependent routing, any special treatment that that device in particular requires or which you've provisioned as a service on your network must be derived from the corresponding address component of your plan. So the device connections are critical in terms of the address that it is assigned or addresses. The router function certainly primarily looking at the destination IP address in each IP packet. in order to route that packet to its intended destination in an efficient manner. But also with source address dependent routing, it's also looking at the source address in terms of being able to apply appropriate treatment of those packets. And then security, once again, to allow or disallow packet traversal based on IP address space. Ingress filtering, those types of things are based on addresses that you want to block coming in on certain interfaces, such as allowing internal address space coming in from externally from the internet. And then other address-based policies like ACLs, filters, and so forth are all going to be simplified through your IP address plan. So for the IP address plan, we make the following recommendations. We recommend that you allocate your address blocks hierarchically. So in video 1, we talked about some of the benefits of this approach in terms of making your routing tables more efficient, your source address policies also likewise very slim and efficient. And so that is definitely one benefit of the hierarchical approach, and I invite you to view that video if you would like, if you haven't already. The second recommendation is to identify these hierarchy layers. So as we looked at in that video, we looked at topology as one aspect, we looked at source address dependent routing as another aspect, so these are certainly key aspects. Anywhere you use IP addresses, security. We also recommend that you allocate on Nibble boundaries. So a Nibble is a set of 4 bits. It's basically a hex digit in the IPv6 address. It's a multiple of 4, and therefore if you allocate on a 4-bit basis along these multiples of 4, we'll see the benefits there in terms of being able to recognize a given hex digit as representing a certain component, either architectural topology or application in your network. And so that can help on the ongoing network management aspect that we talked about. One of the benefits of an address plan can help with that down the road recognition of an address. At the same time, we'll also discuss next allocating on the non-nibble boundary, but we're combining multiple layers in a single nibble, which again is not recommended. If you can keep it to nibble boundaries as per layer, that would be the best approach, but understand that there are cases where you may not have enough nibbles to account for all the layers that you require. So if you are able to keep on nibble boundaries, your maximum number of hierarchy layers is going to be basically the difference between a subnet address, a /64, and the ISP prefix you get, typically a /48, divided by 4. Again, the nibble bits is 4 bits, and then rounding that down, so we end up with generally 4 layers that you'll be able to play with in your hierarchy. If you've got a bigger block from your ISP or what have you, you've got more to play with there. If you do require more layers, as I mentioned, you can combine these into one nibble, as we'll talk about next. Now allocate at the same prefix at a given layer. So this is really a simplification concept, and many of us who've been around with IPv4 for decades have gone through the process of squeezing out every last IP address that we could in order to maximize the efficiency of our IPv4 address utilization. And we did that by using a so-called best fit approach. So you'd create a block, you'd split it successively, keeping large blocks around, so that should you need an allocation in the future, let's say I needed 120 devices in a given subnet, I might allocate a /25. But instead of carving up the parent block into all 25s, I could keep around another 25, 24, 23, etc., on up to half of the parent block size. So in this way, if I needed down the road a location where I needed 250 IP addresses, then I could allocate a /24 from that. So this variable size allocation was really a way to help squeeze out the address space, and keeping these larger blocks around was a way to do that and to provide a best fit type of approach for squeezing out IPv4. With IPv6, it's really less of an issue. There's so much address space out there, and I invite you to really try to delve into the mathematics of it if you can, in terms of the sheer number of IP addresses and subnets that you have at your disposal with IPv6, and where the whole squeezing of every last IP address out of the space is not really necessary or even designed into the protocol. But in any case, we recommend keeping that same prefix length at a given layer. It also keeps things simple. So when you need, 2 years from now, you need to allocate another offshoot of that layer, it's a lot simpler to just allocate that instead of trying to figure out what you've got remaining and carve that up accordingly. We also recommend allocating sparsely at higher layers, and this is not a stringent recommendation. This is more of just some experiential, if you will. And really the idea here is that you allocate space far apart. So instead of just counting from address subnet 0, 1, 2, 3, you allocate really from the beginning, from the middle, from half of that. And so you're kind of leaving space in between each allocation. And the regional internet registries allocate in this manner such that if they do need to make a subsequent allocation, they can just change the size of the prefix. So if they've allocated to an ISP a /32, they need more space, they can just change the prefix to /31 in most cases, doubling their address space without adding a route to the routing tables on the global internet. So that is just a mechanism to spread address space apart, and we'll illustrate that. We also covered that in video 2 of the series. Allocating randomly, this is really at the subnet layer, and this is more of a defensive measure. So pervasive monitoring is a threat. So if you've got a way to kind of hide, if you will, your address space or those addresses that are occupied on your network, should you have an attacker surveilling your network, it's just one other way to add a layer of defense to make those less easily accessible. And then lastly, we recommend tracking your hierarchical address space. We showed an example of this in the first video as well, and really just making sure that you track each block allocation, its child blocks within that layer of hierarchy. So you want to make sure you maintain that roll-up, that aggregation level, and that's really the key benefit of the hierarchical allocation. And so you want to make sure you track your allocations made at each layer, at each branch of that tree that you end up with through the hierarchical address space. So it adds a little more tracking work, but the efficiencies in terms of making your life easier with respect to routing, ongoing network and security management are definitely worthwhile. And if tracking it in a spreadsheet is not amenable, you could also consider an IP address management tool such as that provided by Diamond IP to vastly simplify the process. Now, we recommend allocating on nibble boundaries, again the 4 bits, but here's an example we're going to look at where we can allocate 2 layers within a single nibble. Again, not recommended, but if in a pinch this is something you need to do. This is just an example of the difficulty in recognizing a hex digit as a given meaning that you can get when allocating on nibble boundaries, as we'll see. Just for example, if I allocate sublayer 1 as bit 1 and the other sublayer is the remaining 3 bits within the nibble, I've still allocated on a nibble boundary, but now it's got a dual meaning. And so I can see from the hex value of that hex digit from 0 to 7, I can see that I can at least glean sublayer 1's definition as being a value 0, so whatever you've denoted as that sublayer 1 value 0, and conversely, a value of 1 will be hex value 8 to F. Now, it doesn't say anything about the value of sublayer 2. That is really more than a subsequent exercise that you would have to do to decipher that. It's not obvious by sight looking at the hex digit. If we have to allocate it 2 bits each to each sublayer, then you end up with a little more granularity in terms of the level of understanding what each sublayer refers to. So sublayer 1, again, value 0, 0 is manifested in hex value 0 to 3. And then you can see each of the 4 values of sublayer 2 are going to be within each of these. So value 0, value 4, 8, and C will indicate a common value of sublayer 2. So it's just a little more complicated, but again, an IPAM system can help you keep track of all that. And then lastly, allocating 3 bits to sublayer 1 and 2 bits, or 1 bit to sublayer 2, then you can basically end up with an even versus odd recognition, at least to identify sublayer 2's definition. So allocating multiple layers within a single nibble kind of keeps you to that nibble boundary, which is good in general, but it just creates an added difficulty in easily deciphering by sight, at least perhaps till you get used to it and become a hex whiz. But it just creates just another step that's required to decipher exactly what that means, as opposed to by sight, as we'll see in a few minutes, that can be achieved by an effective address plan. So some of the guidelines: we recommend baselining your current IPv4 address blocks and subnets, pools, individual address assignments, even DNS information, and baselining that really not so much to replicate that with IPv6. Again, you've got that vast address space. You don't need to do a best fit kind of squeeze every IP address out of your v6 allocation. So you really want to take a fresh approach, but at the same time, the IPv4 plan indicates where you do need IP addresses where you have them today. Presumably, if you're allocating a dual stack approach to start with, you're going to need to have IP addresses where you already have them. And this provides a good way to at least get a set of achieving that first goal of an IP address plan in terms of providing that IP address capacity to your infrastructure and user devices. The second approach, or the second guideline, is really to define what address space you want to use. So your public global unicast address space, the GUA, is what you would get from your ISP. It's globally routable. You know, in the spirit of the internet being an end-to-end protocol, IP being an end-to-end protocol, it's recommended that you basically deploy GUA address space throughout your enterprise. Some people are a little wary of this, just given the whole comfort with private address space internally and using a NAT to translate to public externally. And that's really where private, unique, local address space comes into play. So that's where you could deploy private space and perhaps use network prefix translation. But again, it's not recommended by the internet community. It's really more of a public end-to-end approach. But again, it's really a comfort level as well. Also, if you're using some v4, v6 coexistence address space, certain types of technologies, translation, tunneling, mapping type of technologies use certain dedicated address space, so you might also account for that. And this is really kind of your starting point of your address plan in terms of the different address spaces that you'll need to allocate throughout your network. Identify your topology. So again, as we saw in video 1, topology can really be made more efficient from a routing perspective by hierarchical address space, so that's really going to be a key ingredient in your address plan. Also, another key ingredient is perhaps the address-based policies that you may need to enact in your network. So are there source address dependent routing technologies that you've implemented? That should be a key ingredient in your address plan. Any access control lists, any filtering. So for example, if you did want to kind of control access to your cloud private networks, your IoT private networks, certain other partner networks, things like that, that would be a consideration with respect to your address plan from an end user access perspective, from just devices accessing that resource to administrators accessing those resources as well. So anything really based on an IP address, any policy that can be defined on an IP address should be considered there. And it's also the frequency with which you make such policy changes or updates, or need to urgently make a change should a security event occur, for example. So in general, the more frequent or urgent these type of changes that might occur, you want these to be a higher layer in your hierarchy in terms of being able to enact policies quickly. And then those that are inherited, so getting back to the topology aspect, if you've kind of gone beyond the core router size and now you're into the regions and access networks, these are more hierarchical with respect to naturally rolling up uniquely within each branch in the tree, and these can be lower in your tree because of that aspect. Because as we'll see, the lower in the tree you get, the more entries you might have to make to enact a policy change for something common across all of those nodes deep in the tree, as we'll see in a moment. You want to identify DNS information as well, your zones in terms of accessing devices with IPv6 addresses. Certainly you don't want to be typing IPv6 addresses in your browser or what have you. So leveraging DNS to make that easy, adding a quad A record to a given host name. You can use the same host name to reach it by IPv4 and IPv6. So you'll want to take stock of your DNS infrastructure to be able to update that. And again, an IPM system can help automate that process for you as well. Evaluate alternative allocation technologies and techniques. As we talked about in video 2, and we just touched on briefly here, the sparse and random allocation methods are recommended at various points in the tree. You can also use a uniform monotonic. It's very easy, count from 0 on up. Again, just kind of opens it up to potential ease of access from a monitoring perspective. And then best fit, again, is more of an IPv4 construct for address allocation efficiency. Certainly can help you maintain efficiency there, but on the other hand, it could lead to just different size allocations on a layer, which we don't recommend. Again, to keep things simple. Plan to allocate on nibble boundaries, as we've discussed, certainly, and tracking your address space, our final guideline here in terms of tracking it. Because once you define your plan and implement it, as you well know, networks change and morph over time, and so you'll need to update the plan when a new site is open, a new application is rolled out, etc. So these plans need to be very dynamic, and therefore tracking needs to be accurate and kept up to date. So let's take a look at an example IPv6 address plan. In terms of these hierarchy layers, we'll start with an address plan with 2001 DB8 1A/48. And as we look at each layer here, we're going to start at the regional level. So this is similar to how we started in video 1. We'll take a look at our core routers. Let's say I've got a core layer, and I've got my 4 directional allocations. Here I've allocated sparsely, so I've got 8, 4C, and 2 highlighted as the hex digit pertaining to this allocation, as you can see, hopefully highlighted in red there. And the impact there is I've got a single network-wide policy that I can apply with one step by entering this /52 address into that policy. Now if I take within each region a division, and I look at the, let's say in the north region, I can look at operations. Let's say I've got an operations group, engineering group, sales. So here I'm kind of subdividing by organization below region. So I've got, if I do need to make a change to the operations group across my 4 regions, I need to make 4 entries. So the corresponding /56, 8,000 is shown on this picture, but 4,000, C0, 2,000. So that would be basically /56, the 4 policy entries that make if I wanted to enact a change on the operations division treatment or routing, for example. And then maybe by application below that, here I'm kind of randomly allocating within the North Engineering team, which has a block of 8100/56. So if I subdivide that, the next nibble down using a random approach. So the illustration here is showing that, okay, within each region and then within each division of each region, I now have an application allocation. If I did need to make a change or implement source address dependent routing for my voice traffic, for example, I'd basically have to make 12 entries if I've got that voice application everywhere within these 4 regions and 3 divisions. And there may be more in your environment, so that number just multiplies on up. So the thought here is that if you need to make changes to applications frequently, and this comes back to the recommendation in terms of considering what IP policies you have in place, what you might need to change, what you might need to update. This is an area where maybe the application change is maybe perhaps a bit too tedious to make at this stage, at this point low in the hierarchy tree, and therefore the point that the lower in the tree you go, the more entries you might have to make to enact a policy. Okay, let's contrast this with our example number 2. If we start out with the same address space from the ISP 2001 DB8 1A/48, now let's first allocate by application. So here I've got Internet of Things that I want to allocate, wired, wireless. Of course, you could have voice data, etc., whatever works in your network. But again, the benefit here of allocating first is that I've got a single network-wide policy. So if I want to change access to the Internet of Things network, I can basically just enter this /52 as my policy statement and apply the corresponding treatment there, allow, deny, queuing, etc., whatever type of treatment I would like to provide. From there, if I allocate now regionally, so I end up with, within the wired application, I'm going to have north, south, east, and west. So assuming you have applications available in every region, well, then each regional router on the core is going to be communicating the number of applications, in this case 3, routes to reach it. So, for example, the south network would convey the 2001 DB8 1A 8100/56, the C100/56, and the 4100/56 for changes made to the south region for all 3 applications. So those 3 routes would be applied to the south region. So those updates communicated on your core network. So not huge, but again, based on your network, you could have more of each. Now, if we look at the inheritance point that we made on prior slides in terms of each campus residing within each region, so here I've got New York and Philadelphia, for example, and each of these reside within the east region. So my wired east Philadelphia network, 2001 DB8 1A, and I got C, which is wired 2, which is east, and then 1, which is going to be Philadelphia. So you can see how, as you allocate on the nibble boundary, you see easy recognition of each hex digit representing a given component, either application or topology point or whatever IP policy you want to enact at a given layer. It's easily recognizable right in hex digit. And then lastly, if we even go down one more layer to the buildings within each campus, we've got a couple of buildings in Philadelphia, for example. So you can just see how reading that address, you can see the core, the ISP prefix 2001 DB81A, followed by my allocations for wired, which is C, the east, which is 2, the next digit, Philadelphia 1, and then building 2 is A. I've randomly allocated my subnet Nibble for my buildings. So you can see here how if you want to allocate things that you make changes on more frequently or more urgently, how they would be more at the top of your allocation chain, whereas those that are more inheritance-based or hierarchical naturally by topology, for example, they might be a little bit lower in your tree. So this way, if I need to make a change to a building, I just have one entry to make. A campus, I can also make one entry, and so forth. So hopefully that has been helpful in terms of providing you some food for thought for your IPv6 address planning. And to help along the way, we do have a number of free tools that you can access through tinyurl.com/IPv6-tools. We have a needs assessment, which is just a high-level qualitative business needs assessment. We have a simple IPv6 calculator just to play around with IPv6 hex representation and how different networks are conveyed or illustrated. We have a hierarchical address calculator, which is similar to what we just illustrated there, where you can actually look at a given set of hierarchies and the various allocations to make at each level. And that'll give you also a sense. You can do that in force Nibble or non-Nibble allocations. You can get a sense for the ease of recognition or not, and put together various alternative plans, if you like, using that calculator freely. And then if you need to justify IPv6 deployment from a business perspective, you can utilize our ROI calculator to help you as well. So I hope you found this video series useful, and for more information, you can visit diamondipam.com, ipamworldwide.com, and then again, our tools are available at tinyurl.com/IPv6tools.